Swayam Prabha. Digital India. Educated India.
Okay, so here we had a single equal to for every state S, right? So we are translating that into a set of greater than or equal to's, and there's going to be one such line for each state S and each action A. Okay, so these constraints, the good thing is these constraints are now linear, right? That was the whole point of putting in the greater than or equal to here. But then there are nk of them. Okay, there were n nonlinear equations, there are nk linear constraints. Okay, which is good for us, and just verify, right, that V star actually does satisfy these linear constraints. It does. Okay, the fact that it is equal to the max in each case of these actions, right, means that for every action it has to be satisfying at least in the direction of being greater than or equal to. Okay, so the feasible set that emerges by having these constraints, right, is okay for us because we know that it contains V star. If only we could now come up with an objective function, right, that pieces apart V star from the rest of the V's that are there in our feasible set. So again, what's happening on this slide, we are starting from Bellman's optimality equations and trying to derive a linear program out of it, which means trying to derive linear constraints as well as a linear objective function. So the first step we have done here, right, we have come up with a set of n times k linear constraints, which we know is satisfied by V star. But then it might also be satisfied by many other V's, right? So what we need to do next is to come up with a linear objective function, which is maximized by V star, right? And which is not maximized by any other point in this feasible set. Okay. Now this is little more involved than what we have done to come up with the constraints. Okay. So we're going to depart for a couple of slides, looking at a couple of sort of basic definitions and results. Then we will tie that into an objective function which is linear, right, and which gives us V star at the answer. Okay. So brace yourself now for, I don't know, 5-10 minutes of departure. So we're going to now define a couple of things. Okay, so things like V, right, that we've been looking at on the previous slide are mappings from states to numbers, right, or they are n-dimensional real-valued vectors. So let's take any two x and y which are of that form. Now we're going to say x greater than or equal to y. Okay, we'll write this in a slightly funny way with a sort of curl. Just to say that we are doing this for vectors, we're going to say vector x is greater than or equal to vector y if for every state element wise, right, x of s is greater than or equal to y of s. For every element x of s is greater than or equal to y of s. If that is the case, then we are going to say x is greater than or equal to y. Okay, we're going to say x is strictly greater than y. Okay, if indeed x is greater than or equal to y, which means every element of x is at least as high as every element of y, but there is at least one element s for which there is strict greater than. Okay, if x of s is strictly greater than y of s. Okay, this is just a definition for us to compare vectors. If we have policies pi 1 and pi 2, right, sometimes we will overload this notation and say that pi 1 is greater than or equal to pi 2. Right, or pi 1 is greater than pi 2. So when we do that, right, what we mean is that v pi 1 is greater than or equal to v pi 2, or v pi 1 is greater than v pi 2. Okay, so you evaluate the policies and you compare the resulting n-dimensional vectors. If they satisfy greater than or equal to or greater than, then we will say the same for the policies themselves. Okay, so this using this with policies is something we will not really do this time, but we will use it quite extensively next week. Okay. And just to give you some more intuition about this greater than or greater than or equal to. So notice that we can have policies pi 1 and pi 2 which neither satisfy pi 1 is greater than or equal to pi 2 nor pi 2 is greater than or equal to pi 1, right? So because these are vectors, right, it could be that pi 1 is better off in some dimension and pi 2 is better off in some dimension. If you have such policies, they are incomparable. On the other hand, if you have policies that satisfy both pi 1 greater than or equal to pi 2 and pi 2 greater than or equal to pi 1, then it follows from what we've written on this slide that they must have identical value functions. Okay, they might not be the same policy, but at the very least, they will have the same value function. There must be strict equality of the value function. Okay, so this is just defining what it means to compare two vectors using greater than or equal to. Now comes an interesting result. Okay, this is a non-trivial result, but this is something that we will use. Okay, this is what we need in order to derive an objective function for our LP. Okay, so this is the claim that the Bellman optimality operator B star, it preserves greater than or equal to. So what does it mean? Here's the longer form of the statement. So suppose you have x and y, right, which are vectors, and x is greater than or equal to y. Then the claim is that you apply b star to x and y, you will have b star of x is greater than or equal to b star of y. Okay, this is what it means by saying that b star preserves greater than or equal to. I mean, why is this true? Well, this is again something that we can prove using just one slide. Okay, so what does it mean to prove this? So the proof needs us to show that if x is greater than or equal to y, then you compare b star of x of s minus, or rather, right, compare every element of b star of x of s and b star y of s. Okay, so element wise, if we show that each difference is greater than or equal to 0, right, then we will have shown that that's the meaning of showing that b star of x is greater than or equal to b star of y, right? So this is precisely what we will do. Just by writing out definition, this will follow very easily. Okay. One mathematical result again we have to invoke over here is so is greater than or equal to min of f minus g. Okay. Again, something that you can work out by writing down a few cases. I mean, last time we did something like this, we had absolute values. Okay, there's no absolute values involved in this, but this is a mathematical result. Okay, so now let's go ahead and finish up our proof. So if we look at the LHS of this, which is b star of x of s minus b star of y of s, just write down what that means. Right, so you do that by writing down the full form of b star of x of s and b star of y of s. And if you then apply our small mathematical result over here, we are left with this being gamma times min over a sum over s prime. We just sort of used this mathematical result and written down the formula for b star of x and b star of y. But just staring at this hard enough, right, you will see that it is greater than or equal to 0. So why is that? Notice that we made the assumption that x was greater than or equal to y, right? So what does that mean? It means for every element s prime, we're going to have x of s prime is greater than or equal to, right, y of s prime. So there's a non-negative quantity over here that's being multiplied by another non-negative quantity, and that's being added up, right? So the LHS certainly does not have anything in the form of a negative quantity, and therefore has to be greater than or equal to 0. Okay, all right. So we've taken a bit of a departure to introduce this notion of greater than and greater than or equal to, right, to talk about vectors. And here we have shown that if x is greater than or equal to y, then b star of x is also greater than or equal to b star of y. So now let's take this back to our MDP, right, and see how it will help us come up with an objective function for our linear program. So every point in the feasible set of our LP, right, every point V that was in our feasible set, by definition, right, using our constraints, was in the feasible set because it satisfied V is greater than or equal to B star of V. Okay, I mean, this was when we wrote down the linear constraints, that was a way of linearizing the max, right? But yeah, take, I don't know, some time to go back maybe and convince yourself that every point V in our feasible set satisfies V greater than or equal to B star of V. Okay, if that is the case, then let's now invoke the fact that B star preserves greater than or equal to, right? So for every such feasible set point V, we have V greater than or equal to B star of V. So let's apply B star to both left and right, right? So if this is the case, then it certainly means by what we just showed, B star of V is greater than or equal to B star the whole square of V, okay? You apply this both to LHS and RHS, you get this. Again, apply B star, right? You apply 2 times, that's going to be greater than what you get by applying 3 times, etc. And you keep going on in this manner. So notice something interesting. Of course, we've gone from line 1 to line 2 to line 3, but this sets up the possibility of us to do some telescoping, right? If V is greater than or equal to B star of V, right? And B star of V is greater than or equal to B star squared of V, then it means that V itself is greater than or equal to B star squared of V, right? There is certainly transitivity in greater than or equal to. And so if you keep doing this in this manner, we are allowed to conclude that V, right, must be greater than or equal to what you get by applying B star a very large number of times, right? In fact, an infinite number of times. And by Banach's fixed point theorem, we know that if you do it an infinite number of times, then what you have is V star itself, right? Remember that V star was the unique fixed point of B star. So if V is greater than or equal to B star, right, and then you keep applying B star over and over and over again, finally what you get, right, at infinity if you do it, is V being greater than or equal to B star. Okay, so what this means is every point in our feasible set, right, satisfies that every point V in our feasible set satisfies V is greater than or equal to V star. And this is a property that we can milk for linearizing. Okay, what this means is element wise, every element of V is at least as large as every element of V star, right? And therefore, if you sum up the elements of V, right, just do a sum over all states V of S, certainly that has got to be greater than sum of all the elements V star of S. Okay, so the statement here implies what you get by linearizing it in this form. But notice that what's there on the LHS and RHS here is just a linear function of our variables, right? So what we have here is that V star satisfies it, okay? I mean, not V star satisfies it, but every point in the feasible set satisfies it. Okay, so this then gives the form to our linear program. The objective function that we can set up is simply the sum of all the element values, okay? But because of the direction in which we are going, we have to take the negative of that. So if our objective function is minus sum over all states V of S, subject to the constraints, right, then the answer to this has to be V star, okay? So we already showed that V star satisfies these constraints that we did earlier, and what we just did some time back is show that V star must also satisfy the fact that V star is also the quantity that minimizes the sum of its elements, okay, or maximizes minus of that. In fact, I mean, it's not very hard to see, I don't think we did it explicitly, that V star is the unique answer that will come out of this, right? Because if there's any other element in the feasible set, right, that also minimize this, then element wise it has to be equal to V star, right? So the answer has to be V star. So notice that this particular linear program has n variables, it has nk constraints. Linear programming has something called duality theory, okay? So for every such linear program you can create what's called a dual linear program. In this case, we can also actually define a linear program that has instead nk variables and n constraints, okay? So there is also a nice interpretation of that linear program. The answer to that, right, will actually be pi star. Okay, the answer to this linear program which we created is V star. The other linear program which has n variables, right, will directly give us something like pi star. Okay, we are not going to do it, but if you're interested, you can look at the reference. Okay, so again, summarizing what we've done with the linear programming approach, we have taken the MDP planning problem. Essentially, we've started with Bellman's optimality equations and constructed a linear program such that the solution to that linear program will be V star. So how did we do that? We first came up with a set of nk linear constraints, okay, one for every state action pair. That's what you see over here. Thereafter, we said every v that satisfies these constraints has to be greater than or equal to v star, right, in terms of this vector greater than or equal to, which means if you sum up the element-wise values, right, that is also going to be greater than what you get for v star, okay, and that allows us therefore to set up a objective function which is just linear, right, which is just the sum of the element-wise values in v. Either you can minimize that, or if you adopt the old convention of having a objective function you maximize, you just put a minus in front of that. Okay, so that's what we have done on this slide, and we have essentially shown that the answer to this linear program is v star. Okay, all right, so that pretty much completes what we wanted to do with linear programming too, right? So what have we done in this lecture? We have taken up two planning algorithms, value iteration and linear programming, and shown, right, in both cases that the answer that they compute will be v star, from which we can get q star and pi star. As the sort of basic fundamentals for that, we needed to look at Bellman optimality equations, and the fact that the answer to that was the unique fixed point of the Bellman optimality operator. Okay, and the proof that it was the unique fixed point was a consequence of Banach's fixed point theorem. Okay, so what we haven't done is the third family of algorithms for MTP planning, that is policy iteration. That's coming to you next week. Okay, and I know that the other IOU is the actual proof, right, that the pi star that was greedy with respect to v star was an optimal policy, that you can't have policies that are better than pi star. That will follow very naturally as a part of the analysis of policy iteration, okay, through what's called the policy improvement theorem. That's coming to you next week. Okay, so good, we're done with week 5 then. See you again in week 6.